Okay, so in today's video we are going to talk about the external reaction and molecular species balance method. The atomic balance method as well as the external reaction method has already been previously discussed in the previous video. So in this particular video we are going to talk more about the molecular species balance. But before that, let's jump first right into the external reaction method first. So as for the external reaction method, we'll first need to actually focus on the molar flow rate of NH3. Okay, so ammonia is burned to form nitric oxide and water. The fractional conversion of oxygen is 0.5. So fractional conversion is actually equivalent to the amount or the number of moles of substance that has been reacted divided by the number of moles of a particular substance that is coming in to a particular system. But it is also can be broken down into in the amount of substance that's going in minus the amount of substance that is coming out of a particular system divided by the amount of substance that's coming into the system. So this is the proper definition of a fractional conversion. So it has been stated here that the fractional conversion of oxygen is actually 0.5. So 0.5 is actually equivalent to in minus out divided by in of of oxygen, because it states here that the fractional conversion of oxygen is actually 0.5. So the inlet molar flow rate is 5 moles per hour for ammonia and 5 moles per hour for oxygen. Calculate the exit component molar flow rate using the tree method, which is the external reaction method. So the first thing that we need to jot down is actually the formula for the external reaction method, which is simply N. So this is the number of moles that, or the final number of moles of the inlet stream, which is equivalent to the Ni naught, which is the molar flow rate, which is the initial molar flow rate of the inlet, plus with mu or V, which is the stoichiometric coefficient, multiplied with the external reaction method. Okay, so Ni dot refers to the 5 moles per hour because it has been stated that. Okay, so we can first actually calculate in terms of NH3 because there are three types of substance here, which is NH3, oxygen, nitrogen monoxide, and water. So let's calculate with respect to NH3 first, ammonia. So Ni naught, which is the molar flow rate, the initial molar flow rate of the inlet stream for ammonia is actually 5. It has been stated that here it's 5, so 5 plus with the V or mu is actually the stoichiometric coefficient of ammonia, which is 4. However, since ammonia is a reactant, therefore it needs to be a negative sign of -4, and I think it's something like this. Should be something like this. So 5 minus 4, this thing, and then let's calculate with respect to oxygen by using the same formula above. Okay, so this one is also 5, it has been stated in the questions, plus with mu is the stoichiometric coefficient for oxygen is 5. However, since it is a reactant, we have to negate it, so it becomes -5, like this. So you can simplify the equation to become like this. Okay, this is the second equation. Now we will be looking at the third equation, which is NO. NO. So for NO, Ni, which is the molar flow rate of the final molar flow rate of the inlet stream, equivalent to the initial molar flow of the inlet stream plus with mu external reaction xi, mu xi. V is the stoichiometric coefficient of NO. So okay, in the inlet stream. So as we can see here that there is no NO or nitrogen monoxide in the inlet stream. Hence, we can conclude that the initial molar flow rate of NO nitrogen monoxide in the inlet stream is 0. So 0 plus with the stoichiometric coefficient of NO is 4. So just put it for positive 4 due to the fact that nitrogen monoxide is a type of product, so it is positive, it remains positive because it is a product. So this is the third equation, and then we also have to take a look at our water. Ni given to Ni naught plus with V xi. Okay, this one is 0 because there's no water initially. There's no water on the left side of the equation, there's no water, so just put it 0. And the stoichiometric coefficient of water is 6, and since water is a product, just put it as positive, so 6 xi. And then okay, and then let's take a look at, and since okay, so oxygen, it has been known that the inlet molar flow rate is 5 moles per hour for ammonia and 5 moles per hour for oxygen, which means that initially the molar flow rate of oxygen in the inlet stream is 5 moles per hour. So we already know the amount of oxygen that's coming in is 5. So by using this particular formula, the fractional conversion formula, 0.5 is equivalent to in, which is 5 moles per hour, minus with out, which we don't know, divided by 5. So 0.5 multiplied with 5 is equivalent to 2.5, equivalent to 5 minus out. Okay, so rearrange the equation. Out is equivalent to 5 minus 2.5. So 5 and 2 minus 2.5 is equivalent to 2.5 moles per hour. So this is the amount of oxygen that is coming out in the outlet stream. So 2.5 moles per hour it is. So let's take a look at our, this one is water, NO, and let's take a look at this one. So if you can see here that Ni is like, so we can actually substitute the, see 2.5 here. This is the amount of oxygen that's coming out. So 2.5 we can put it here. You can substitute it because this one is actually the final amount of oxygen that's coming out. So you can just simply substitute it right here. So 2.5 is equivalent to, okay, it's 2.5, just want to double check on that. 2.5 is equivalent to 5 minus 5 xi. So 5 xi is equivalent to 5 minus 2.5. So 5 minus by 2.5 is equivalent to 2.5, and 2.5 divided by 5 is equivalent to xi, which is equivalent to 0.5. Yeah, I think 0.5. So xi is equivalent to 0.5. So the only thing that you need to do is for you to take this value of xi right here, which is 0.5, and you just substitute it here in the xi section in the xi. So for example, if you want to find the amount of NH3 that's coming out in the outlet stream, then you just substitute the amount of xi here and you shall get the correct amount. So 5 minus 4, this one is 0.5, it's equivalent to 5 minus half of 4 is actually 2, so 5 minus 2 is 3, so 3 moles per hour for NH3. And then this one is 0.5. Okay, so for oxygen, 5 minus 5 multiplied with 0.5, so 5 minus with 2.5, so 2.5 it is. So 2.5 moles per hour of oxygen is coming out in the outlet stream. And then we also have nitrogen monoxide. So nitrogen monoxide, just substitute 0 plus for 0.5, so half of 4 is actually equivalent to 2, so 2 moles per hour of nitrogen monoxide is coming out in the outlet stream. And last and but not least, finally we have this one, 0 plus 6 multiply with the value of xi, which is 0.5, so half of 6 is 3, so 3 moles per hour for water. So that's it. Those are the value of the outlet streams for for water, nitrogen monoxide, oxygen, and ammonia. Alright, so let's now moving on to the, if you watched my previous video, I already discussed about the atomic balance approach and I do not want to repeat that. So let's take a look at the molecular species balance approach. Okay, so as for the molecular species balance approach, okay, let me just drag this one up here first. Okay, so as for this one, for the molecular species balance approach, the fractional conversion of oxygen, right? The formula that I mentioned just now is that it is equivalent to the number of moles or the molar flow rate or whatever of the substance that has been reacted divided with the amount of substance that is coming in, or that enters a particular system. So it has been known that the fractional conversion of oxygen is 0.5, and we also know that but we don't know the amount of the number of moles of oxygen that has been reacted. We don't know that, but what we do know is the fact that 5 moles per hour of oxygen is coming inside, so we can just put it 5 here, because 5 moles of oxygen is coming right into the system, which means that if we rearrange the equation, so 0.5 times with 5, we shall get 2.5. So 2.5 moles per hour is equivalent to the amount of matter that has been reacted. So this is the amount of oxygen that has been reacted in the particular system, right? Okay, so what we do is that, okay, we do know that in minus, okay, the amount of oxygen is coming in to a particular system minus with the amount of oxygen that has been reacted in the system will be equivalent to the amount of oxygen that's coming out from a particular system, right? So for example, if oxygen is coming in and then some parts of it reacts with some other substances, so if we have the difference between the amount of oxygen that's coming in with the amount of oxygen that has been reacted, we will be able to get the final amount of oxygen that's coming out from the system. So which in this case, in our case, we have 5 moles per hour of oxygen that's coming in, but we don't know the amount of reacted. Actually we do, so we just found out that 2.5 moles per hour of oxygen has been reacted, which means that if we must subtract 5 minus 2.5 is equivalent to 2.5 moles per hour. So this is the amount of oxygen that's coming out from the system. Okay, so this is our first answer. And then we do have, actually we have oxygen. We start with oxygen because it has been given that the fractional conversion of oxygen is 0.5, so that's how we actually manage to get the amount of oxygen that's coming out in the outlet stream. And now let's moving on to the ammonia. Okay, so for the ammonia, so from the previous, just now that we already done, we already know that 2.5 moles per hour of 2.5 moles per hour of oxygen has been successfully reacted with ammonia, which means that whatever I mean which means that this can tell us that the same amount of moles is equivalent to the is equal to the amount of ammonia that has been reacted with oxygen. So to put it simple, 2.5 moles per hour, right? 2.5 moles per hour of oxygen, we divide it with 5. Okay, 5 is the stoichiometric coefficient of oxygen, of O2. So we divide it with 5, and then we'll multiply it with 4, so that we'll be able to get the number of moles of ammonia. So, and we shall get 2.5 divided by 5, then multiplied by 4 is given to 2. So 2 moles per hour. This is the amount of ammonia that has been fully reacted with oxygen. Okay, this one is the amount of ammonia that has reacted with oxygen, and we already know previously that the amount of ammonia that's coming in minus with the amount of ammonia that has been reacted should equal to the amount of ammonia that's coming out in the outlet stream. So the amount of ammonia that's coming in is actually 5 moles per hour, and we subtract it with the new information we get here, which is 2 moles per hour of ammonia that has been reacted with oxygen previously. So we shall get 3 moles per hour for the amount of ammonia that's coming out in the outlet stream. So this is for ammonia. Okay, so this is our second answer. And then we shall apply the same thing to nitrogen monoxide and water. So we just take the same data, which is 2.5. 2.5 is actually the amount of oxygen that has been reacted with ammonia just now. So 2.5 divided with 5, and then multiply it with 4, because we want to find the number of moles of nitrogen monoxide. So we multiply with 4. So 2.5 divided by 5 multiplied with 4 is given to 2. So 2 moles per hour. This is the amount of um, NO, nitrogen monoxide. This is the amount of nitrogen monoxide that was generated, that is produced, that is generated from the system. So this is our third answer, and it has been stated earlier that the stoichiometric coefficient for, or the number of moles of water that has been produced is 6. So we just do the same thing. 2.5 moles of oxygen that has been reacted with ammonia earlier, we multiply it with the 5 moles of oxygen from the equation, then we multiply it with 6 because 6 moles of water. Okay, and we shall get the amount of water that has been produced, and that brings us to 3 mole per hour. This is the amount of water molecule that this is the amount of water that has been generated by the system, and this is our fourth answer. So there you have it, and that is how you solve this particular question by using the extended reaction method and the molecular species balance approach. You can take a look at the atomic balance approach from my previous video. Right, so peace out.